So here go two examples of applications of solving logarithmic and exponential equations. Just as a little review, we have already learned this. So simple interest would be interest that is compounded once at the end of the year. And compounded interest is when it's compounded more than once per year. And when interest is compounded continuously, this is how we could figure out the amount after some amount of time. So here is our question. So you get to invest $5,000 at 5% compounded continuously. So you're going to earn 5% per year of this, but it's compounded continuously. So it actually ends up being more than 5% after the end of the year because you earn interest on the interest that you've already earned. How long will it take for your investment to double? To double meaning go from 5,000 to, yes, you guessed it, 10,000. So, using this, we can say that the amount is equal to the principal, meaning how much you invest, times e to the, and then interest rate, 5% is 0.05 t. So this is an equation that would give the amount you have if you invest $5,000 after t years. And what we're looking for is how long will it take, so we are solving for t, for your investment to double, meaning the amount is now 10,000. So 10,000 equals 5,000 e to the RT. So the difficult part of this type of question is probably reading through it and interpreting what it's asking and how to set that up. Once you have it set up, based on what you already know, you can probably solve this. So we're solving for t. We have e to the something, so we know that base to exponent, the variables in the exponent, so we will be taking the log of both sides. But we want to isolate the base to exponent, meaning get rid of this. So if we divide both sides by 5,000, we're going to put 2 equals e to the RT, so 0.05 t. Because we have base to exponent all by itself, now we can take the log of both sides. So let's see, log of 2, and you know I'm going to use ln because it's going to make it a little easier, because ln of e is 1. So natural log of 2 equals natural log of e to the RT. So ln of e to the something is something. I'll write that. ln of e to the something is the something. That's always true. And so what we get here is natural log of 2 equals 0.05 t. So let's use the calculator and figure out what natural log of 2 is. ln 2 says 0.693147, and we're going to divide that by 0.05. So it looks like, whoops, let's get some ink in there. T equals 13.8. I know that looks like a 6. 0.86 years. Okay, so not bad. I would love my investment to double. And if we think about it, so if you just earned 5% every year and you wanted to get to where you had 100%, meaning doubled your investment, it would be 20 years. But the fact that you're earning interest on your interest on your interest means it only took 13.8 instead of 20. That's, it's a lot of time. Cool. So that was example 1. Here's example 2. So half-life. I know this is a lot of words here, but here's what we're talking about. You probably learned something about this in both biology and chemistry, radiocarbon dating, etc. But the idea is that when something is radioactive, within the nucleus there are protons and neutrons. So carbon, for example, normally The atomic mass of a carbon atom is 12 for the majority of them, but some of them are heavier, meaning they have extra neutrons. And so this naturally occurring radioisotope, C14, it's actually in our bodies, it's in all organic things, and it decays. So we say the half-life, this is kind of the bottom line here, the half-life of carbon-14 is 5,730 years. What that means is it takes this much for half of it to decay. So it's like there's this much carbon-14, right? And after 5,000, where's my eraser? Oh dear. Great. Let's try this again. So there's this much carbon-14. Aha! And after 5,730 years, there is this much. And then after another 5,730 years, half of that would decay. And then after another 5,730 years, half of that would decay. And then after another 5,730 years, half of that would decay, etc., etc. So, what's up with this equation here? The amount equals the original amount, which is just like what we had over on our previous page. Amount equals principal times e to the times some base to the rate times time. So very similar here. We have the amount after some time passes, original amount, base. Notice here for half-life that the base is a half. That's not a coincidence. Half meaning every time we multiply by 1/2, the stuff is cut in half. Okay, that was a great explanation. And then t divided by 5,730, meaning if we plug in 5,730 for time, then we're multiplying by 1/2, etc. So this in general is how we could write a half-life equation. So here's our example. Polonium 210 has a half-life of 140 days, so that's pretty radioactive. Suppose a sample of this substance has a mass of 300 grams initially. So you, your enemy gives you this present. Here's 300 grams of radioactive polonium, and we're going to find a function m of t, m for mass as a function of time, that models the amount remaining after t days. So after t days, so let's say we have mass as a function of time equals our, so this equals our original amount. Our original amount was 300 grams. We're talking about half-life, so our base is 1/2. And notice up here we had we had years here, and this is basically the half-life. So time here was in years. If we know that our half-life is 140 days, we could have our exponent be t over 140, where t equals days. So do you see how when you set up an equation, take a basic value like 140, plug it in, we have an exponent of 1, so we have 1/2 to the 1 is 1/2, meaning our amount, the mass, would be 150, which is half of 300, so it makes sense. Okay, so here's an equation we could use. Find the amount remaining after 1 year. So after 1 year, time, the number of days, would be 365, and this is going to give us, we're solving for mass, the amount. So we could say m of 365, meaning the amount after 365 days, equals 300 times 1/2 to the, and then what do we have? 365 over 140. Okay, let's see what our calculator says. So I'm typing in 300 times, and then in parentheses, 1 divided by 2, and then to the, and 365 divided by 140. Don't stress about the leap year, 365.25 or whatever. So I type that in as 100 times 1/2 to the, and then 365 over 140. And enter. Let's see, what's our guess? I'm guessing 100, no, 75. 49, okay, that's what I meant. So, M of the amount after 1 year is 49 point, what did I say, 2 decimal places? So we got a 2, 4, and what are we talking about here? Apples? No, we're talking about grams of polonium. We started with 300. After a year, we would have this much. So, now I think we're going to solve for the exponent. Let's see. How long will it take? Yeah, so we're solving for t. How long will it take for the sample to decay to a mass of 200? Meaning the amount is 200. So let's check it out. 200 equals our original amount. Our base for half-life is 1/2, and time over 140. So we're solving for t. We got all this jibber-jabber. We want to isolate the base to the exponent before we take the log of both sides. So we're going to get rid of that 300 by dividing both sides by 300. Yes, you guessed it. So 0.66 equals 1/2. Very funny. T over 140. Alright, this is where we can take the log of both sides so that the exponent can be moved down to be a coefficient. So it looks like the log of, I don't like that number. I'm going to leave it as a fraction. Log of 2/3 equals, and watch me skip a step here. Yeah, we can take it. Our exponent, log of 1/2. We have done several questions like this. So again, our exponent came down out front. That's right here after we took the log. So our exponent was here. We brought it down right here. We're solving for t. So first let's get rid of this log of 1/2 by dividing both sides by that. So log of 2/3 over log of 1/2 equals t over 140. So I'm going to calculator this and then multiply both sides by 140. Maybe we'll just write that in. Times 140 times 140. Kaboom. So again, let's look at our question, because it's always, it's fun to sort of anticipate what the answer is, but it's also great to develop some number sense and, see, like when you get an answer, if if I get 1,000 years here, is that appropriate? No. How long will it take for the sample to decay to a mass of 200 grams? So we have something that starts at 300 and has a half-life of 140 days, meaning after 140 days, it's going to be at 150 grams. So we're wondering how long it takes to get to 200 grams to decay to 200 grams. So we're expecting something less than 140 days. All right, good. Now we can get an answer, and hopefully it makes some sense. So, that's what I meant. Calculator. Let us see. We got log of, in parentheses, 2 divided by 3, and divided by log of, in parentheses, 1 divided by 2. So that is giving us, this is looking good, 0.584962500.7, and we're multiplying that by the 140, so 140, so let me be clear. This is what calculator told me for this. I'm going to multiply that by 140, and we're looking at 81.89, and remember our units, we're talking about days. Alright, so we were expecting something less than 140. Looks good. Pat yourself on the back, and have a good day.